Good afternoon, everybody. I'm Boelo Schuur. I'm Scientific Vice President of the European Federation of Chemical Engineering, the EFCE. I've been in the board of the EFCE since the beginning of this year, and I'm a chemical engineer by training. I received my degrees from the University of Groningen in the Netherlands, and I built my career in academia. I have been at the University of Twente since 2011, where I climbed the ranks, and currently I'm a full professor. And my chair is called Sustainable Separation Technology. I'm very happy to be involved in the introduction of this webinar on sustainable recycling of plastics, and I look forward in participating in it. Let me first say something about the Spotlight Talk series. This is now the 5th year of our Spotlight Talk initiative, which started in 2020 to keep the community together during pandemic times. The success of the previous years convinced us to transform this Spotlight Talks into a regular series that occurs 2 times per year in the years that we do not have a European Conference on Chemical Engineering, and once per year in the years that we do have the ECCE. And in this year, an even year, we do not have an ECCE. This means that we, next to the spring series, have also a fall series of the Spotlight Talks. And this today is the first of our fall series. And we have in total 13 of our working parties and sections participating in the coming 2 weeks. Sustainability, mixing, electrochemical engineering, high pressure technology, food, loss prevention, and safety promotion in the process industries, agglomeration, multi-phase fluid flow, static electricity in industry, education, polymer reaction engineering, thermodynamics and transport properties, and early career chemical engineers. They all deliver over a 2-week span very interesting spotlight talks with leading industrial and academic experts. The series also enables attendees to sample matters in new areas, encouraging cross-fertilization of interests. The complete program is available on the EFCE website, and in due time, also these recordings will be available on YouTube, so you can watch it another time. And the EFCE promotes scientific collaboration and supports chemical engineers in over 30 countries, representing more than 100,000 chemical engineers throughout Europe. The EFCE's working parties and sections cover all major specific aspects of chemical engineering and are in fact the core of the organization of the EFCE. They provide an important forum for the technical exchange and networking among chemical engineers in Europe, and I'm particularly happy that in this series of Spotlight Talks we will have the first contribution of a newly established section, the section on sustainability, with one separate Spotlight Talk and another co-organized on the Working Party on Education. Before concluding, I would like to thank all the people who worked hard inside the working parties and the sections of the EFCE in general. But very specifically, I would like to thank Martina Poo for arranging everything to make these Spotlight Talks happen. I thank you for your attention, and I give the word to Antonis Kokossis, the chair of the section Sustainability.
Yes, good afternoon, everybody. Before I start my presentation, I would like to thank Martin Poo and the French delegation for diligently organizing, managing this beautiful series of spotlight seminars. Through her compassionate and charitable efforts, she and her team have enabled the European Federation to communicate with a much wider audience, and ever-increasing audience, and cover topics across this wide range of working parties of the Federation, setting up a series of seminars that set up, if you wish, some sort of legacy for the community. So my thanks to that. And as I continue, I further take pride to introduce the sustainability section of the European Federation, a section that is dedicated to one of the most cherished topics of our discipline. And the section has been set up recently, as well explained, and at this time, I would like to extend my thanks to our president, Giorgio Veronese, who has been instrumental in the development of the section for its concept and launch. And before I start my presentation, I would like to give you the link for the sustainability section, and we encourage you to go and visit this place since we have these events, the two events, essentially this spotlight seminar commences the first round of seminars today and as we continue for the next days. But we are committed to continue this round of spotlight seminars in the spring. And we have prepared, so this is a site for the section. And we have prepared also to receive your own feedback as to what you want as a preference to see from our own seminars in the future. So this is a form that you are encouraged to fill in, either at the sustainability section or just by copying this particular link. And let us know what kind of things, and priorities you would like to see in the following future seminars of sustainability. With all that, I would like to continue with my presentation, which is based on a technical review. This is policy material that I'm presenting to you that I delivered myself earlier this year at the European Union Parliament by invitation, more specifically at the Plastics and Waste Management in the Circular Economy session that is organized by the Committee on Petitions and the Environment, Public Health, and Food Safety. In that session, some of us were invited to assess and present material to explain the position about plastics in the future, sustainable perspectives in the context of circular economy, and present sustainable solutions or outline solutions that point to better technologies and better management. So I use this presentation today, if you wish, or this presentation is intended, as an introduction to the overall problems that we will cover and review in the sustainability section as material for my other two speakers, who will enter after me. So I'm tempted to reason with the common jitters we have about plastics. There are definitely alarming figures behind plastics in their production and recycling and disposal of plastic. And with a risk to reiterate on what you may already know to some extent, I wish to remind you that in an era of climate change concerns, and even though plastics are entirely dependent on virgin fossil resources, or almost entirely dependent, production of plastics has essentially doubled since 2005. And if you go back in time, after World War II, you will see that we have a 20-fold increase in the last 50 years. As we travel around in Brazil, in India, in places where waste is not managed properly, we may think that it is these countries that produce most of the waste and the problems, with plastic waste. But but indeed, in our advanced countries, the production of waste is 20 times more than what it is for the other countries. Now, for someone who, like myself, dwells in a country surrounded by sea, it's frightening to know that a full truck of plastic garbage almost enters the sea every minute. And extrapolating this figure to the future would see oceans with more plastics than fish in 2050. The innocent bottle, which I have on the left corner, is producing a wasteful make waste kind of practice. And I think that the make waste model that we have for the plastics is largely the one which is responsible for the problem we have. 30% of packaging is never to reuse, and 14% is collected for recycling, but not necessarily recycled. And if you see the recycled figures of plastics as against other kinds of material, metals come to 76%, paper 83%, glass 73%, and plastics only 40%. And again, the bottle that I have, in the lower corner is using about for a bottle there, it is using 7 liters of water and 120 milliliters of oil. And behind this production is non-fossil based material like benzene, ethylene, propylene, naphtha, and propane are used. So plastics are there to drop and replace, or it's time to reconsider their engineering. And probably this is the time to think about the good things of plastics. Plastics are inexpensive, cheap. Probably this is the reason we don't care to recycle. They are also versatile, lightweight. They can adjust their properties to the different applications. And okay, we can ban plastics, but if we replace them with other solutions, glass, paper, aluminum, sometimes and most times, I would say, the life cycle analysis behind these kinds of actions would show that our kind of carbon footprints are essentially increased rather than decreased. So the problem is that the plastics are produced in this way, that are produced in a wasteful way, in the linear way, in the uncircular way, wasteful way. And one should consider all these different actions which relate to the raw materials that we need to use, and materials which relate to plastics should rather come back to the production. The landfilling and incineration of plastic is apparently not a solution. And new technologies that I'm trying to point out with you will be the way we think about that. So this is the global picture behind plastics. And this here, the numbers that I cite come from Helen MacArthur Foundation, in case there is a need to double check. I mean, the big picture is that fossil-based non-recyclable material is used with a huge kind of amount of material which is processed every year. It's amazing that 1/3 of that ends up into sea. 1/3 is almost landfill, and the other 1/3 is either going to landfilling or moving or struggling its way to recycling. But actually, only 2% of this kind of material comes back to the production. The breakdown of plastics are shown on the right. Apparently, packaging plastic accounts for 61 to 69%. And if you account for others, which is unclassified kind of plastics, this with unclassified plastics would come to 75% of the overall production. Now, there is a framework that we are developing in the European Union, and you are probably aware of. And this framework had started earlier on with targeted directives for packaging waste, for landfilling, for the shipment of waste, for promoting light waste packaging. But after 2018, and in response to the United Nations Sustainability Directorate goal, we have, a targeted objective for the big picture. And the big picture, again, what you see as 2018, addresses circular economy and is trying to see the problem in its entirety, in the picture I was showing before. So it is promoting circular economy. It is targeting specific plastics like PET, like polyethylene, and is targeting also technologies that will try, we would need to try and strive to promote and develop, in the future. So, these are promising targets, 50 to 55% improvements for the next 5 years or so, which is significant. But the question is, are we prepared to meet these targets? So here comes, the alternatives that we are we have identified as important directions to develop. The first comes with alternative renewable feedstock. So the feed has to be more renewable, and that includes, plastics that we have produced, recycling, chemical recycling of plastic, but also including, waste-based material like CO2 as options, to consider. In terms of the technology itself, One could identify two different major categories, one that relates to the materials itself, the other one relates to the way we design the particular object article that relates to polymer. And in the first category, one is trying to extend the lifetime, use material, and compare material usage over performance, increase the recyclability. So you may be using a low quality material or lower performance, but enable the polymer to be recycled back to processing, or the use of other technologies like nanoplastics and matrices that enable durability without having to rely on large quantities of the plastics itself. And probably here it's fair to note the other major initiative in the European Union, which is the Circular Plastics Alliance. Many people are not probably aware of that. It's a pledging campaign launched in the plastics industry, and that one complements the Commission's effort to improve plastic waste management with an objective to integrate 10 million tons of recycled plastics into products by 2025. That means by next year. The Commission has addressed the places again, identifying a gap between the amount of recycled plastic companies pledged to provide. This is about 11 million again, and the amount pledged to be used, with 4 million tons of recycled materials, currently used per year. And it is an initiative which is major and involves about 225 actors. So this one is more or less committed not to just have targets and vacant word, but demonstrate the chemical recycling of plastics, in the future. So what we are heading to are this kind of picture. So instead of having fossil-based material, this is one, we also want to involve feedstocks which are renewable. But there would be a very limited amount of how much we can replace the fossil-based feedstock. So we rely very much more on the chemical recycling of the plastics that we produce, and this is 4. We want also technology to manufacture plastics reusable and recyclable, by design, and this is 2. We want to take plastics many more times in reuse cycles without having them to worn out. This is 3. And we want technology to facilitate recycling. Again, this is 4. And since we prefer plastic, apparently we prefer plastic cycles, but this won't be possible. So we accept that some streams of this kind of revised kind of supply chain would enter as raw materials to other production, and this is fine. A lot of ambition, but how close we are to deliver this kind of progress. So let me first start with one, which is the renewable feedstocks. So here we have a long list of potential renewable feedstocks, and this comes from the Research and Innovation Priorities of Circular Plastic Alliance, the CPA I mentioned before. So we have technologies for packaging, PLA. We have alternatives for plastics in building and construction, starch-based chemicals. We have alternatives for automotive, for electrical and electronics. We have alternatives for agriculture, medical, healthcare, as you see on the table. The promising leads include FDCA for NOx, PEFs, that could replace PET, or mucinic acid that could replace polyamides. C6 and C5 sugars are used for several options and lignin to aromatics. And there is a challenge to cope with their complex matrix, improve energy and process efficiencies related to the fractionation of these chemicals. The integrating cascade catalytic process pyrolysis that I will mention close to the end of the presentations can build also blocks for ABS, polystyrene, PET, and polyolefins. There is a wide range of TRLs in this category from 5 to 9. The TRLs extend, to this other table, and alternative feedstocks there on the table also consider the use of CO2 as a feedstock for the production of plastics. This is still uneconomic, and we need more demonstration and scale-up facilities. We have successful cases of natural fibers combined with bio-based thermoplastic matrices. Is the Schuur success story? But again, this relates also with the cost for CO2 capture, and technologies for CO2 capture are very much related to the viability of the technologies to produce plastics from CO2. But over there, we have also promising leads, and these include polycarbonate alcohols, the etherols, or carbonates, polypropylene carbonates, and polyesters. So this is a narrow TRL from 5 to 7, as I said, less kind of developed and mature technologies. I also have, I mentioned solar pipe before, but there are more examples from what SMEs can do, and I note some of the cases here. Boelo, the Dutch company of Just Eat food delivery platform that you may know, produces alginate sachets to contain sauce and water, replacing single-use plastics. And these are, novel, material, as well as Appeal, which is a plant-derived coating to slow down water loss and oxidation. And they can replace, wrap, shrink wrap with very promising LCA performance. Or we have cases like Lush, which is a UK-founded company with more than 800 stores, which essentially is trying to eliminate packaging, altogether using electronic platforms, for delivery. Now, I come to the technology part, which again, other than the renewable feedstocks we mentioned before, plastics are to be produced with better functions for circularity. So here are the key aspects are plastics which should be durable, recyclable, and easy to dismantle. We have two parts there. The ability of the plastics to repair and preserve polymer properties. There are cases also, technologies for self-healing polymers, which are based on Diels-Alder reaction or thiol exchange reactions. And this range in a lower kind of range of 3 to 5. Or improve aging of plastics, so that plastic can withstand extreme conditions. And in this case, of course, we have the support of plastics with matrix structures, and nanomaterials, becomes part of the solution. This part of circularity is particularly important for multi-layer and complex plastics. Ideally, you would like the plastic to be, strong and durable, but also be able to degrade on demand. Polyethylene, polypropylene kind of chains are very durable, can withstand, but on the other side, they don't have the chemicals, the components where we can break the chain, and take back the polymers. In the future, this kind of monomers could be rebuilt, so the recyclability can be easier, and the chemical recycling can be easier, to achieve. Compatibilizers are a nice way around that. These promising lines that essentially convert a multi-layer of plastics into mixtures of plastics with cross-linked functions. So essentially, you have a mixture of plastics out of which you can take back the individual monomers. And also thermosets based on chemically modified polymers, such as polystyrene, can facilitate thermal degradation, not affecting their properties. Biodegradation is a big topic, but is also misleading. Plastic which is biodegradable, that means, doesn't mean that it is recycled. A bio-based polymer is always recycled. A biodegradable polymer is not always recycled. And, there are some also concerns on how the biodegradability of polymer, addresses properly environmental aspects. In other words, the polymer may dissolve in the sea, but nobody knows how it affects the ecological the ecology and the communities in the sea. So let me now go to another topic other than the technologies involved. Another part is the use of business models. And business models essentially can be applied as early as yesterday. They can manage cost, and they can use of digital applications and platforms to their benefit. You can classify them into two major categories, refill and return kind of models. In the refill kind of models, the user retains the ownership. They can refill either at home or on the go. So users, refill usable containers, at home and keep, the vessel, or they can use it at places, where in-store kind of dispensing systems are available. The return model has been not as favorable in the past because it was considered to be burdensome, and confusing. But now it's becoming more popular because the producers or the companies can also monitor the customer profile through the kind of involvement of user, in this platform. So this, also holds advantages further than the environmental, priorities that we mentioned before. Now there is plenty of room to incentivize the deployment of reuse models, and ERPs, apparently should be connected to that. There is a drive to connect with economic incentives and directly involve sectors that make use of plastics, let's say the agro-food chain or leisure or tourism that make or associate with heavy use of plastic can become part of the supply chain and incentivize or be incentivized, by the business model so that they credit the users for or their customers for involving more heavily into their businesses. So there is a potential there to quantify, reuse, and recycle streams, say monitor volumes or create observatories, if you wish, that could report progress of each one of these sectors and give them credit on the basis of their performance. I would like to continue with the challenge and the economics of circularity, because today the typical cost of managing waste is connected only with the weight, not connected with the reuse or recycling. So again, there is no credit to circularity and any sustainable practices. The cost charged by weight. So a 500 milliliter PET that is decreased from 24 grams to 9.45 grams gets a lot of credit, for this reduction. But less material may translate into weaker bottles, so less lifetime and loss of recyclability. So sometimes you think that you do something good, but essentially you do something bad. Countries like Germany and Holland also have promoted eco-modulation of peat to promote recycling. So they have already started doing things towards this direction, transferring credits from waste to energy installation to reuse and recycle promoting. And I'm referring to two major kind of schemes, the Dutch Packaging Waste Fund and the Deposit Return Schemes of Germany, that has reached a collection of PET as high as 80%, with some significant investment, of course, from Germany, which is about 800 million per year. Now, I will continue Yeah, I will continue with a few words about sorting and collection, which is important in order to secure that you have good quality recyclable polymers, to reprocess. The two typical technologies include wet and dry sorting. Dry sorting, as you know, is mostly based on optical technology, mass spectroscopy, um, near near infrared spectroscopy, NMRs, and optical spectroscopy like visible, for instance, are typical cases. Whereas wet kind of sorting includes the use of solvent, solvation, and flotation. There are challenges there. Some technologies are pretty mature, so TRLs are close to 8 or even 9 in most cases. But there is room there for the case of multi-layer plastics. The multi-layer plastics impose a challenge for this area. Multi-layers or multi-polymer structures are some of them plastics, are difficult to separate because the properties of the individual polymers are so different. So in this particular case, you can think of dynamic cases of dynamic crosslinks, as it is for thermosets or fiber reinforced polymers that enable the chemical separation of the matrix from the fiber reinforcement. And that could be, innovation technology there at a higher level, almost 8. The most challenging part, I think, is the chemical cycling. And over there, you have a number of technologies that you can consider. Pyrolysis is an general kind of technology, plasma assisted or microwave assisted, and this can be applied to a number of plastics, but not giving back the monomers. In the case of polyethylene or propylene, for instance, it gives oils and waxes that are not the material that you need in order to recycle the polymer. How to say? Polymers that have attractive sealing temperatures like polystyrene or methacrylates or PET can actually be decomposed, degrade into the individual monomers, and then these monomers can be separated. And then cases, you can note there is the Agilix, which is demonstrated in Oregon, if I remember well, where they have scaled up the technology, and challenges are mostly on the separation of the downstream effluents using distillation or similar other techniques. The switch to monomers through solvolysis and depolymerization is relatively developed for some polymers, such as PET or polyamides or polystyrene. And as stated, they are lacking behind for polyolefins. The chemical recycling of mass consumption plastics like polyethylene or polypropylene result in, as I said, value products such as waxes or oils that are not the ones, to consider for recycling. Gasification processes, conventional gasification or plasma assisted, can possibly be combined with biological and chemical post-treatment. They show a wide range of TRLs, while currently pilot and demo plants are under investigation. Both recycling technologies, pyrolysis and gasification, can recycle plastic waste to chemical building blocks, especially for polyolefins. This might be viable options. And biotechnological processes for plastic wastes valorization are currently very, very low, TRL 2 or 3. More fundamental research is apparently needed in this area, but the life cycle and also actually CO2 kind of footprints, which are summarized on the right, show that how much or how important these technologies can be as you move from incineration. Remember, this is where we stand today, to cases of mechanical recycling or pyrolysis or solvolysis, essentially accounting for a tenfold decrease in the footprints that we produce. Now, the pyrolysis, as I said, is possible with or without catalysis. Pyrolysis of mass consumption plastics like polyethylene or polypropylene, resulting in defined value products such as waxes. But catalytic pyrolysis seems a viable route to plastic waste recycling. Integrated catalytic pyrolysis maximizes product value with high benzene, toluene, and xylene content. In other words, a mixture of chemicals out of which we can produce again all the monomers that are used in this area. Solvolysis is a topic that you will see in the presentation, some sort of solvolysis that will come just after me. So I will skip this part for excitement. I guess Dimitris can say more about that. In my concluding remarks, I would like to stress that there is a strong hope and promise at all levels for major advantages. And there is also a need to modulate financial incentives, with less credit to waste management, but reuse, but credit for reuse and recycling. And also, it is important to connect the polymers supply chain with other kind of sectors, the users, of plastics, so that you can incentivize the reuse and the good recycling flows back to the process. And apparently, digital technologies can play a lot in this effort, since they can provide cost-effective means to communicate, interact across the different sectors. So with all that, I believe that sustainability section has a role to review and keep you up to date as to how we develop and progress towards this direction, especially the chemical part of that, which is fully justified by the European Federation of Chemical Engineering, is the one responsible, to report, about emerging and promising technologies. And I believe that we will see two of them in the next two presentations that follow mine. Over here, I just cite the different sources that we use, in the study that I present to you, including the Ellen MacArthur Foundation, the Plastics Europe, white papers, from the SASCHEM group, and so many others. In case that you want more details or you want me the references for the things that show in this presentation, please feel free to contact me. And with all that, I would like to thank you and conclude, my part, giving the podium to my colleagues for the rest. Thank you very much. Hello?
So maybe I continue.
Yes, I think it's the Andreas or Dimitris. I'm not sure.
Antonis, just one comment from my side. I have introduced this webinar, and then I give you the word as the chair of the meeting. So I cannot continue to join this webinar due to having other obligations. Yeah. From now on, please preside this session forward, and you introduce the other speakers as well. Thank you, Antonis.
I think, yeah. All right. So, let me, let me introduce the next speaker, Andreas Kuenkel. Andreas, please share the presentation. Andreas is the Vice President of Biopolymer Research at BASF. The title of his presentation is Biodegradability 2, a holistic approach to degradation in natural and engineering environments. BASF is one of the, if not the most active company in chemical recycling. Andreas, correct me if this is wrong. And we're looking forward not to listen to your presentation.
Yeah. Thank you very much for this kind introduction. Can you see the presentation?
Yes,
okay,
we can.
Good.
Yeah.
Okay. So I will continue in this session. And what I would like to address is, if we look on the overall picture, we have already seen the topic of technical recycling, but there is another option when it comes to end of life, and this is the biological recycling, biodegradability, and this will be in focus of my presentation, and I will explain you when it makes sense and how to balance this with technical recycling option. And the example I will give you, and I want to explain this, is the mulch film. This film is applied in agriculture. And as you can see here in this introduction picture, a mulch film has different kind of advantages. So in the beginning of the season, it helps to generate a warmer climate from the plants. They can grow better. It helps also to keep the water because the water cannot evaporate through the film. And the third big advantage is the control of the weeds, so you need less herbicides. So we have here different sustainability benefits, and on the other hand, also increasing the yield of the plants. And for this mulch film, there are two options possible. The first option is a polyethylene film, and the second option is a biodegradable film. So through the whole process, this is very similar. The only difference is when it comes to end of life. So the polyethylene film is collected and afterwards recycled, whereas the biodegradable film is plowed into the soil and then biodegrades, and the soil is ready for the next season. And there is one important aspect I would highlight today, and this is the sustainability and environmental performance and the resulting requirements. And this is a very good example here, because if we look on the polyethylene film, to recollect and to recycle, you need at least to have a thickness of 25 micrometers. This means it is nice that you can make a polyethylene mulch film at 8 micrometers, but with this you will not achieve a sustainable performance. You need at least 25 micrometers, and this means to achieve the environmental performance, this is defined then by the mechanical requirements. The biodegradability as end of life allows you to make the film as thin as possible, and the thinner the film, the faster it biodegrades. And I would like to concentrate today on this option, on the biodegradable mulch film, and to show you the benefits of this. To do so, we first have to understand what is biodegradability. And it's always helpful to start with ourselves. So most of us will have had lunch. So at this point of time, what you are doing is you process the food biopolymers from your lunch, mainly into energy, to listen to the presentation and then contribute to the discussion, and as side product, CO2 and water. But a certain part needs also to be converted in cell material, so to renew, for example, our skin cells. For microorganisms, catalyzing the biodegradation, it's absolutely the identical process. With one exception, they can use also synthetic biodegradable polymers if they have the right structure to convert it into energy in cell material. Second point is what is important to consider: biodegradation is a process. If you look here on the bottom, and as an example here, one biodegradable polymer, for microorganisms, it's a huge structure. They cannot take this structure up and digest it. they have to apply a trick. Similar, if we eat a pizza, we take fork and knife and cut it to smaller pieces. So the microorganisms excrete enzymes, and these enzymes then help to break down the polymer into smaller pieces, and these smaller pieces can be taken up and be biodegraded, as said, to energy, CO2, water, and biomass. This is a very complex process, and it has two elements. And this you can see here in this slide. The two elements and purposes are, on the one hand side, to develop appropriate materials which are performing chemically wise, but on the same time are biodegradable and long-term to reduce the carbon footprint to become bio-based. But on the second side, it is very important to have appropriate standards of biodegradation which define the materials which are accepted or materials which cannot be accepted. And this needs a lot of understanding, and our approach, and I will show it also in a minute, is to combine biodegradability with chemistry through different digital tools. More on a scientific basis, you can see here some more details. So if we look on the biodegradation, it's very important not only to understand the biology, but also to have appropriate analytical tools to follow the pathway of biodegradation. This is one level of science. The other level of science you see here on the top. It's very important to have test systems correlating what is happening in the laboratory to the field, because otherwise it's not possible to develop appropriate products. So how does it look now for the biodegradable Malchfilm? And I would like to give you here this example, what we have done in the recent years, also in the cooperation with the ETH in Zurich. So if we look on the biodegradation curve, what you can see here on the left-hand side, after 180 days, so after 6 months, 90% of this biodegradable Malchfilm, consisting of 2 biodegradable polyesters, are converted into CO2. That's very good, because this also fulfills the requirement of the standard, which is 90% in 2 years. And for this, you get a certificate. Nevertheless, the question we got immediately from the European Commission was, where is the rest? Where is the rest? 90% is nice, but if 10% is the rest, and you do this for 50 years, that's a lot of stuff. So please show us, where is this rest? And this was an intense question, also as part of the microplastic discussion. And microplastics have been also mentioned in the previous presentation. So that was the question. And to answer this question, which is finally the question, where does the polymer carbon end up? We worked for more than 10 years with the ETH Zurich and evaluated this process in all details. So the first thing to do that was to define a labeling method which allows to follow the fate of the carbon atoms. And we decided to take a 13C labeling method because this allows you to work much more practical in the laboratory compared to the traditional C14 labeling method. And then we looked into the details of the process, and I will not go here into all the different aspects, but starting from colonizing, cutting down the polymer, and then metabolizing it. And due to the labeling here indicated as the red star, it is possible to follow the fate of the polymer. And I will concentrate today here on these two aspects, CO2 conversion and microbial biomass. So this is the showing the conversion into microbial biomass. And what I would highlight here is also the charm of the C13 labeling method, because it allows you to mark each monomer at different sites, so you can also follow individually the fate of the biodegradation of the individual monomers. So what you do is the only growth substrate is the labeled biodegradable mulch film, and then you can detect where the carbon is going. Here you see the setup at the ETH in Zurich. So here these bottles where with soil the biodegradable mulch film labeled is incubated. But this does not answer the question, what is the complete fate of the material? And therefore, as stated in the beginning, the textbook tells you it should go into microbial biomass, but so far this has not been shown. Again, you can see here the polymer we are talking about, and I will not go into all the details. What is important, and first I would like to put your concentration here in the middle. In the background, you see a gray, shiny structure, and this is the mulch film. And on this mulch film, you see two structures. First, these lengthy arms here, these are fungi. You know from your kitchen if you keep your bread too long. Or here, some smaller structures, these are bacteria. And both are involved in the biodegradation process. And now comes here on the right-hand side, the decisive picture. With this method, the labeling can be transformed into colors, and the base labeling is 3%, and therefore the background appears here, background, the mulch film, appears here in this intense green color. And all region where labeled carbon is accumulated appears in red. And you can easily see that especially in the fungal region, there is a lot of red. And that was for the first time the scientific evidence that carbon from a synthetic biodegradable polymer is converted into microbial biomass. And this helped us also a lot in the discussions in Brussels, because then also the politician says, okay, now we understand your basic concept. The significant part is converted into CO2, and the other part goes into microbial biomass. In addition to these methods, we also investigated different soils and complemented this recently also with field trials in Switzerland, and identified more than 700 microorganisms being capable of breaking down and metabolize these soil biodegradable mulch films. So overall, if we come back to the concept I showed you at the beginning, for this case study, in all areas, all requirements are fulfilled with respect to the scientific evidence that this end-of-life option is truly working. So the pathway is understood, the test systems are correlated, we have a standard, and the results are published in scientific journals, which is essential to have a fact-based discussion. As part of this, very important, what I would like to mention, the role of polyesters. So polyesters are very versatile systems. And the system we use here is a system which is composed of butanediol, adipic acid, and terephthalic acid. But the advantage of this Lego system is you can change the different monomers, which then allows you not to have only different properties, but it also allows you to increase the bio-based content, reduce with this the carbon footprint, or to modify your biodegradability, which allows you not to be only biodegradable in soil, but also biodegradable in compost. In addition, of course, polyesters are very suitable materials also for a technical recycling, what we see with PET, but also now starting with polylactic acid. As you can see, this system here, the polyester system, allows you a lot of variations. And to be faster in the product development, what we have developed in the recent years is a computer model of predicting biodegradation. So what is done in this model? So if you have a new structure, the first thing what you have to do is a certain amount of very accurate biodegradation tests. You have to analyze this data in a very appropriate way, and you need a computer with sufficient capacity. And then with the help of smart computer scientists, you can develop models which predicts you the biodegradation. And the result is shown here on the right-hand side of the plot. So what you do is you plot the real values of the biodegradation experiment with the values of your model. And if the model is perfect, everything will be here on the orange line. And in this case study, you can see we are roughly at accuracy of 90%, which is very, very good. And with this model systems, we are very confident that it will be possible to develop not only in a faster, but also in a more appropriate way, new polyesters, new biodegradable materials, and as said in the first presentation, to really live sustainability by design in an appropriate way. So to summarize this, so what is the conclusion? And I think this example shows you there are different circular options for the mulch film. In one case, it can be a biodegradable mulch film, as shown you in this presentation, but also fulfilling sufficient mechanical requirements for polyethylene mulch film, being thicker than 25 micrometer. This allows to recollect this mulch film and then go into a technical recycling. And I think, therefore, this is an example, and I would like to use here the case study of Austria, where in a constructive discussion, it was discussed how to improve the use of plastics in agriculture. And the conclusion was, which at the end looks quite simple, to say, if the mulch film is below 25 micron, then it should be biodegradable because it is not possible to collect this material. Whereas if the requirement for the material for specific plants is above 25 micrometer, it should be a polyethylene mulch film, which is then collected and technically recycled. And what we can learn here from this example is that we should extend our view from the classical material perspective, looking on certain polymers, but when we look on the end-of-life options, we come to a different perspective, and we can also learn from this example there are no good or bad polymers. There are polymers which should be used in an appropriate way, and then different options are possible. It can be a biodegradable material, or it can be non-biodegradable polyolefins, but if they are correctly used, they can both contribute to a circular economy. Thank you very much, and I'm open afterwards for further questions.
Thank you very much, Andreas. It's excellent talk. I mean, we have questions for all of us, I guess, mine as well. So again, I would like to thank you again, Andreas, Dimitris, and myself. Let us go through what was posed as questions for us. We'll start with myself. The question has been from Eldan. What do you think about EU's initiative to connect cups to the bottles so they won't be thrown away on their own? That's nice question, I guess. Probably how to start. Maybe useful to remind people who are not familiar with the cups that this kind of material can be of several resources, can be, polypropylene, can be high density or low density polyethylene, can also be PET, and again, Dimitris, who is more familiar with TB, can correct me on that. And why we sort it, we should remember why we sort it, or would they ask us to sort it, because there are apparently different paths, from PET as against polypropylene or high density polyethylene. So apparently by removing these caps, you help the sorting process. But this is, again, a trick question because in the sense there could be technologies, that can combine, sorting, for these polymers, without having for us to remove it. I recall there has been such technology on flotation where, for instance, high density polyethylene, has been removed from flotation naturally from PET, so you didn't have to separate it. And, I guess other kind of technologies could be thought along these lines. I don't know whether I'm answering your question, Eldan. But the question is that, well, actually, this is a typical case why, a new technology can make the reuse kind of path, can change the reuse path and prevent or bypass something which was a necessary step beforehand. So, I mean, going back to your question, my view is that if there is no technology to separate, then this is a good reuse strategy. If there is technology to separate efficiently, so you can skip this kind of part. Then I have another question, I guess, for me as well. I do not see how the use of nanoplastics can contribute to sustainability. And will the nanoplastics be harmless to the environment? I mean, that's again, all these questions, we have to be, brave and honest, I guess, when it comes to this new technology, because we need new technology, but we should not be afraid of that. Now, the motivation for nano structures, are obvious, I guess. They are intended to strengthen the properties of the product. So use less material, also may be easier to trace and in the collection stage. But apparently, in order to control the improvement of the nano enforcement and the polymeric matrix interface, there is a need apparently to improve the chemical compatibility and dispersion stability, as well as increasing mixing efficiency when necessary. So the answer is, the question actually is, your question is similar to mine. Are they indeed better? You have to see and assess, the overall thing, life cycle analysis of the alternative cases, whether the material is recyclable, or whether the material kind of losses could be more damaging to the environment, because you will always have losses, in the recycle process. So you have to think about this careful, but it does make good sense for me. We can follow up, on that, but the whole idea again is you use less material with a better, nanostructure that, ensures durability, and good properties and structures. So on that basis, it does make sense. Now we have questions I will go through one by one. Well, I guess that was for Andreas. Can you please put the presentation for more? And then Ahmed is asking whether your figures on alternatives for evaluating, do you have any figures, he's asking, Ahmed, on uncertainties for evaluating the biodegradation yield? Andreas, this is a question for you. Do you have figures for uncertainties on biodegradation yield?
What is meant with biodegradation yields?
The efficiency of biodegradation processes, and whether you have figures on uncertainties, whether, in other words, the biodegradation as a process has uncertainties, or whether you have uncertainties to review.
Maybe the 90% plus or minus what? Maybe that's what the question is.
It was
okay.
Maybe.
So, yeah, okay. Let's say this is the basis that a certain part of the material is converted into CO2 and a certain part is converted into biomass. This, of course, can vary also dependent on the environment where you are in, and how fast this biodegradation process takes time. For soil and also for compost, very probably this ratio of 9:1 is quite appropriate. Yeah, if you go to sludge, the amount of biomass can even be higher.
Yeah.
Hope this answers the question.
Yeah, I mean, that's to me, but the questions continue. Ahmed again, whether what are the main parameters that allow modeling of biodegradation and where further scrutiny is needed? I guess, yeah, extending your answer, I guess.
Okay. I think the important parameters to come to appropriate model is first to understand the chemical structure of a polymer in a quite appropriate way. Yeah, and this is, I think, a big task for modeling because the descriptors for polymers are not so well established. Yeah, this is the first thing what has to be considered. Because a polymer has different molecular masses, and this has to be brought into the equation. Then, of course, it needs an excellent understanding of the biodegradation process. So where are the bonds are broken? What are the different intermediates? With what speed does that happen? And then to combine this, and especially this part of the biology needs a lot of further elaboration. The models for biodegradation of small molecules are well developed and also well accepted, but the transfer to polymers is an ongoing work and it still needs time. But with the examples I have shown you, it is really possible that a model tells you quite exactly if you exchange monomer A to B, what is the effect on biodegradation and how to design the structure in a more appropriate way.
Thank you, Andreas. Andreas, is more for you. It says polymer. Yeah, I mean, congratulations for your presentation. And the question is, if biodegradable polymer gets mixed, collected with a regular polymer, does this negatively affect the recyclability of the normal plastic?
This is a very, very good question. Yeah. And maybe you can also, and Dimitris can also step into this question. So, as I have said, I think polyesters are quite appropriate materials for recycling. Yeah, what we see with PET materials, I think, is with what you mentioned with respect to the collection rate in Germany and the recycling rate is very, very good. Yeah. So I think it's a matter of the amount and then of the selection of the respective polyester. So for example, if you have polylactic acid materials in a recycling process, if you collect them appropriately and put them into a recycling stream, my hypothesis, which is in difference to a lot of German recyclers, I have to say, but my hypothesis is if it's a polyester or polyolefin, you have to collect it, you have to separate it and bring it into the right recycling stream. Whatever the technology is, Dimitris has shown different technologies which are possible. But from the bond itself, I think what we have to keep as a chemist in mind, a polyester bond by itself is weaker than a CC carbon polyolefin bond. That's the chemical nature of the molecule. So therefore, the molecule is very suitable for recycling, for different recycling technologies. But maybe you can add, Antonis and Dimitris, to this question.
Let us first, if you don't mind, go through the remaining questions. You know, I guess that one is not for you, Ned. I mean, it's for Dimitris, where the question was, well, can you please give the scale of emissions, Dimitris, on page 7 of your presentation? So you go back.
A very short answer is no. That's why I removed it. Because it has to do, it's not a, it's a consequential LCA, so it depends on the end of life. So I don't want to go into the details of that one. But the relative scale is correct.
Okay, thank you. Then the other point from Janos, very interesting, the topic of PVC during the presentation and not cut options for recycling. Are there any? options for
recycling of PVC.
It's
Yeah,
about the
specifically,
PVC.
my experience, I guess, with the Procter & Gamble company is that we don't work on PVC, so that's why I don't have anything in terms of PVC. So that's so I'm not familiar with it. I don't know the subject.
You have attracted so many questions, so I go on with you. It says the next question is from Dario about the type of solvents that you use for polypropylene recycling. Are you prepared to you know?
Yeah, I cannot go into specifics, but I can say alkane solvents.
Okay, and you stop there.
Yep.
Okay, a question for Andreas again. So Andreas, stay tuned. How do we manipulate polyesters effectively to achieve, biodegradability?
So maybe the simplest example is if you use PBT. PBT is a non-biodegradable material. But if you introduce into PBT adipic acid and you come to a PBAT, then you come to a biodegradable polyester. Yeah.
Mm-hmm.
So it's about how to introduce certain monomers into the backbone. And the key is, and this is also the difference between a PBAT and a PET, is how flexible is the polymer chain so that it can enter into the catalytic side of an enzyme. Yeah, and the more flexible the chain is, then you increase the biodegradability. And you can look into the design of the polymer and then modify it. And you can have also a variance between different monomers, either increasing or even further increase the biodegradability.
Thank you. Ahmed, this is to Dimitris now, not to Andreas. He insists on the solvents, but I guess you answered already. You're not going to say more than that. You mentioned advantages. This is anonymous.
Maybe, Adonis,
yeah.
Maybe the question was their fate as well. So I can say that the solvent is recycled.
Okay. Their fate.
So you make sure that the solvent is purified, of course, and then the end of the process is recycled back to the beginning. Yeah.
Okay. Now we'll stop here. So, an anonymous, you mentioned the advantage of the solution recycling. What are some of the key challenges and disadvantages? So, in other words, you have disadvantages, you have toxic solvents, energy intensive process, I guess maybe expensive or energy intensive, just tell us. And also, could you elaborate on how food grade recycling was possible for polypropylene?
I mean, you can put as a key challenge there is to operate the solvent in the process. So that would be one there, and the other one is that you need to prove, I guess, to the FDA that you have food grade recycling process. I mean, the last part of the question is food grade recycling to polypropylene. When you do chemical recycling, for example, pyrolysis, you make the recycled naphtha, and then you blend it with the fossil naphtha. You go to the steam cracker, and you make ethylene and propylene. So it's very easy to prove that this is food grade polyethylene, polypropylene at the end. Where in this specific case, with the FDA protocol, you have to prove to the FDA that you have removed the specific materials, the specific ingredients, the specific chemicals that you need to remove to call it food grade recyclable material. And as I mentioned at the beginning, P&G licensed the technology to Pure Cycle Technologies. So Pure Cycle Technologies is an independent entity. So that entity did all the work on the food grade recycling for polypropylene. But it's fair to assume that they have proven to the FDA that they remove all these impurities that they have to remove to call it food grade. Energy intensive. It's less energy intensive than the other processes, as I mentioned in the graph there. It's more intensive than mechanical, of course, but it's less intensive than pyrolysis. Toxic solvents? No, it's alkane solvent that's been used in making polyethylene and polypropylene all the time.
Okay. Next question to you as well. In terms of negative emissions technology, what are some examples of carbon capture? I guess the
you can think of direct air capture is one example. Direct air capture, you capture air for carbon dioxide from the air. Granted that the concentration of CO2 in the air is about 420 ppm. The alternative is to capture CO2 from smokestacks. In that case, the CO2 concentration can be 20%, 10%, 20%, that level. And as you understand, there is a difference in cost between one process versus the other. Whenever the concentration of a gas is very small, the cost in terms of energy and money is going to be much higher than when it's 10 to 20%. But these are examples of carbon capture.
Well, and again, the other question is not for us, it's for, but yeah, for Ms. Poo. I mean, it's about certificates and this kind of stuff. So Martin will answer, I guess, this one on our behalf. I have a question for Andreas. Andreas, you mentioned about, biodegradability and the biochemical, cultures, decomposed polymers, yeah? I mean, how do you target the proper microbial populations in order to, to do the work? And how much, you can expect, from an effort to design your own microbial cultures to target the polymers. In other words, can you reverse engineer the whole thing rather than you test, an existing, microbial culture, you go and develop one that fits according to your application? Is there a path in this way?
Thank you for this question. So first part of my answer is, for example, what we see in soil, that there is a sufficient number of microbes present in the soil which are capable of biodegrading this material, because the material is food for them. Yeah? And they are so smart then to capture this as a material. But of course, you can think of not only of microorganisms, but you can also think of enzymes being involved in the biodegradation process, to use that also for other purposes, for example, for PET recycling. So I think recently the first pilot plant for enzymatic PET recycling has been started. So this means the understanding of the biodegradation process of microbes and the respective enzymes can be used also more in an engineering technical pathway. Yeah, but so far, at least we and all the other companies involved, we have not followed this potential road of adding microorganisms either in the soil, in compost or wastewater treatment plant, because the microbial communities are so fit to adapt. And especially if we look into the wastewater microbial communities, this is a continuous development of the population. But in principle, this is possible. And for example, to increase the methane yield in biogas plant, this is done. Yeah, you add certain microorganisms which help to better biodegrade the material to generate more methane.
My question partly is motivated by the fact that we can build biochemistries. I mean, we have custom-made biochemistries according to what we need. So if we know what we need, in theory, we can go back and produce, the microorganism that will attack the particular part of the carbon chain so that they could decompose into what we want them to decompose into. So this kind of opportunity exists there, but only in theory, because it's in a forward way. You test things that people develop rather than you go back and explore things.
This is valid. Nevertheless, our preferred way is to design materials based on a knowledge which have the capability then to be biodegraded in an appropriate way. Yeah, and so to adapt the materials and use the natural microorganisms, which are very, very capable.
Yeah, and nature is your guide to that, I guess.
Yeah.
So, I mean, other questions, we don't have any other questions. I don't know whether, you have questions for Dimitris or Dimitris has questions for you, or, we have a forum open to whoever else, wants to inquire more. Otherwise, we can call it a day. Martin?
Yes, I'm here. Okay, I think now, yeah, if you are finished, we can conclude. Say a few words, and thanks all the participants for attending
Yeah,
the webinar.
again, yes. I mean, it has been great pleasure for me, not only because, we had these two excellent presentations, mine has been more or less an introduction, to the overall problem of bioplastics, and plastics in general, not bioplastics. But I would like to remind the audience that we are planning to have other sustainability kind of topics and encourage them also the ones who were late and didn't get the first announcement that we made, that sustainability section has also a place for you to report preferences about future spotlight seminars that you would like to see addressing sustainability. Plastics will definitely be also in the spring, as we have discussed, Martin. But also there is scope apparently for other topics. We encourage everybody to go there and mark the ones that are preferences for them. With all that, I would like to thank you again and congratulate you for managing all the spotlight seminars. And yeah, I mean, all has started, with you, and it continues so nicely with you. So thank you very much, Martin, for guiding us, through that. With all that, I would like to conclude. We have nothing else. I would like also to thank the audience for the questions and the active participation during this session. So,
Thank you.
thanks. Have a nice day
you.
to all of you. I guess you will watch the elections, Dimitris. Everybody will be watching you today, yeah? So, good luck to your whatever choice is yours.
Bye.
Have a good evening.